Hello. Thank you for everyone to be here. It's 10 a.m. Eastern Time in Boston, Massachusetts. My name is Philippe Clemenceau from Axiom Optics, and we're here for this webinar entitled A Practical Tour of Adaptive Optics. We're going to give this a few minutes. Please stay put. More people are connecting right now. I think most people are on mute. I hope the sound quality is good. I hope, if you have adjustments to make right now with the speakers and so on, please do so. And then through this event, please feel free to write your questions. There is a section here on GoToWebinar for questions. Don't hesitate to use it. There will be 2 Q&A sessions through this event and 2 live demos. Maybe, I don't know if we can actually see the camera right now with the people who are going to do the demonstration. Hello there. So the organizers of this webinar are right here. So to the right is Guillaume Dauvillers, Chief Technical Officer at Imagine Optique in France. And to the left is Xavier Levesque. Sorry, I should say it with the right pronunciation. Chief Scientific Officer at Imagine Optique France. There you go. Hello, Xavier. And there's going to be Jerome also, Sales Manager in the US for Imagine Optique, and myself, Philippe Clemenceau. It's 10:03 a.m. So I think maybe we should start. This is actually the 3rd webinar of a series of 3 webinars on wavefront measurement and adaptive optics. So the first one was on wavefront sensing and accuracy of wavefront sensing. The second one was on optical metrology based on wavefront sensors, and this one is now on adaptive optics. So we're here to show you a practical tour of adaptive optics. And for those who know or who don't know, adaptive optics is used in many different fields today, mainly biomedical imaging, for example, ophthalmology and microscopy, but also optical coherence tomography. It's, of course, has been used in astronomy. I think most people know very famous images that have been done with adaptive optics. And then, of course, it's also used in telecommunications and lasers, mainly for beam corrections. And Imagine Optic has been an innovating leader in adaptive optics. It actually offers a very unique universal platform for adaptive optics, compatible with deformable mirrors and special modulators on the market. And in this webinar, we will show you some examples of applications, and we will show 2 live demonstrations. Okay. So Patrick, let's go to slide 2, which shows the outline for this 1-hour webinar. We're planning to spend a little bit of time on slides, hopefully not too much, probably around 15 minutes. And then we'd like to, have most of the time allocated for the demos, right? So we'll see Guillaume and Xavier actually manipulating and showing you all the different aspects of the software and how the beam gets corrected, how the point spread function, how good it is, and so on. And but first, I'll introduce the companies. Setup, and then after that, we'll go on the setup. So setup one is actually a low-speed AO loop that we use for teaching adaptive optics. Setup two is also a low-cost, fast adaptive optics loop that could be used on a telescope, for example, to correct atmospheric perturbation. So these are very good setups to actually know about. And then we'll conclude with closing remarks. There are going to be 2 Q&As, one at the end of each setup. And again, please feel free to write your questions. So slide 3. So yeah, for the presentation of Axiom Optics, Patrick. Yep, there you go. Thank you. So for those who do not know us, Axiom Optics is actually a US spin-off of Imagine Optic. We started in 2010, and we're not just offering Imagine Optic products, we're actually a full-scale distributor of high-end optical instrumentation. So some of you might know us for our activities in wavefront sensing and adaptive optics, but we also offer microscopy solutions, different cameras, scientific CCDs, CMOS, and SWIR in-gas cameras as well. Beam characterization solutions, beam profilers, as well as pulse measurement systems. Metrology solutions. And adaptive optic solutions, of course, and as well as positioning hexapods. So I encourage anyone, of course, to go on our website, www.axiomoptics.com, and discover all the things we offer in the US. Next slide, please. Now let's focus on Imagine Optic. Imagine Optic is based in Orsay, France, south of Paris, has about 50 employees, and is an innovating leader in wavefront sensing, metrology, and adaptive optics technology. Imagine Optic manufactures Shackleton wavefront sensors, turnkey optical metrology and adaptive optic systems based on wavefront sensors as well, and deformable mirrors. Imagine Optic has a very knowledgeable and strong competency in software development, engineering systems on request, and provide services to industrial customers and research organizations. Imagine Optic products today, and probably most of you today are already users, the products of Imagine Optic are used in research labs and production facilities around the world. And then for the next slide, I'll pass the microphone to Xavier, I believe, who will start on the principle of adaptive optics.
Hello. So adaptive optics, the concept is quite simple, and the goal is quite simple too. You have an aberrated wavefront incoming in your system, and you want to have a perfect wavefront at the output. To do that, you need basically 3 elements. The first element is the wavefront sensor. The wavefront sensor measuring the aberration, then the software calculates the correction to be applied to the deformable mirror, and the deformer takes the opposite shape of the aberration, and the combination of these gives you at the end a perfect wavefront that can be focalized in case of laser in order to have the best and the highest intensity on the target, or can be used for imaging in microscopy, in bioscience, or even for astronomy. Let's see some example of adaptive optics. First of all, we would like to present some results in retinal imaging. On the left, you have the state-of-the-art of retinal imaging. And if you zoom, you can see that the image is quite blurred with high resolution. When you use adaptive optics in order to correct for aberration of the eyes, you can have the best and a sharp image, and the zoom of this image is here, and you can see individual cone photoreceptors. That is to say that with adaptive optics, you are able to see retina at cellular scale. Another example in bioscience is microscopy, adaptive optics for microscopy. In this case, adaptive optics can help you to see quite deep inside the sample. Indeed, when you want to go inside the sample to image your object, you will have some mismatch index, and that will bring some aberration. And if you are able to correct for those aberration, you can have a huge improvement in your signal-to-noise ratio. And then, if you have this improvement, you can have a sharp image inside the sample. And you do have here two examples of this. On the left, without AO and with AO inside the sample, and you can see that the signal-to-noise ratio improvement is more than a factor of 6. Another example in microscopy is adaptive optics for multiphoton confocal and light sheet microscopy. On the left, you do have a multiphoton microscope with on the left part without adaptive optics, and on the right part with adaptive optics. And as you can see, the image is brighter and the details are much more clear with adaptive optics, because we are able to adaptive optics is able to correct for all the aberration of the system, and especially the aberration given by the sample itself. On the right part of the slide, you have another example of adaptive optics with light sheet microscopy, and with and without AO, and you can see a huge improvement in both in signal but also in resolution, thanks to adaptive optics. I will give the microphone to Guillaume de Villers for further example of adaptive optics.
Yes. Good morning, good afternoon, everyone. Here is an example of how can be used an adaptive optics closed loop for ultra-intense laser. This is a picture of the pole which contains two beam lines, two 10 petawatt laser in Romania, on which 6 adaptive optics closed loop are installed, 3 per laser. And maybe I can just focus on the last stage of adaptive optics system. It is very close to, it is installed very close to the last experiment, just before the experimental chamber, in order to remove the aberration coming from the chain, in order to focalize the beam as best as possible in the experimental chamber. So because of misalignment, optical defects in the beam line, and thermal effects, some aberration may appear, which destroys the trail ratio and therefore decrease the intensity on the target. As you see here, adaptive optics allows having a nearly diffracted limited point in the target, which allows to reach very high intensity up to 10 to the power of 22 watt per centimeter square. This kind of lasers are used to study matter and interaction between laser and matter. All these three applications we just saw, Imagine Optics have solutions in terms of wavefront sensors, in terms of deformable mirroring software. For the last application in astronomy, I just chose an example of, in my point of view, is the best adaptive optics system for astronomy. Here are the pictures of the instrument, which is called Galaxy. It's a very big AO system installed on one of the 4 ESO very large telescopes in Chile. On the left side of this slide, you have a picture of the secondary mirror, which is in fact deformable mirror. It has a diameter of 1.2 meter and more than 1,100 items. As they want to see objects that are very far away from bright stars, they use laser guide stars. So they send light in the atmosphere to create artificial stars that are used to measure the wavefront. And in this configuration, they have 4 Schackerman wavefront sensors in order to measure the wavefront and calculate the correction to be applied to the deformable mirror. On the right part of this slide, we have the image of Neptune acquired with the system with adaptive optics and without. But what is interesting here is if we compare the image acquired by the system with the image acquired by Hubble, we can easily see that the resolution given by an adaptive optics system can give better results than the Hubble telescope. Let's enter into more detail on what happened in an adaptive optics in terms of command control. I try to summarize in one single equation what are the main parameters and what is the principal equation that guides the system. First, we have the command at the step I. This is the mirror previous position. And second, we have the command at the step I+1, which is the mirror new position we want to calculate. And of course, there is a correction term consisted by the wavefront, which is actually measured by the wavefront sensor, and the 4 parameters, the wavefront target. This is an important parameter. As you see here, if the wavefront measured is equal to the wavefront target, the command on the mirror won't change. That means the mirror won't change its shape. But if there is an error between the measurement and the target, of course the mirror will move. And this is done by matrix multiplication and a fixed parameter, which is very important. You have to keep in mind that an adaptive optics system is a closed loop system, and as all this kind of system, the adaptive optics need a gain. The gain is between 0 and 1. If you use 1, as you see, you apply directly the measurement difference into a change in the mirror position. If the gain is 0, nothing changes. Usually for fast adaptive optics, mainly for astronomy application, the gain is between 0.3 and 0.6, because above 0.6, the system is unstable. There is a fifth parameter, which is very important. This is a command matrix, which is obtained by calibration. Xavier will present in detail this. In fact, we will not measure directly the command matrix, but we will measure the inverse, which is the interaction matrix. And the 7th thing I want to focus on is that there is a minus sign here in this equation because we want to correct the defects and not to amplify it. So let's see on the setup one, and I'll let the mic to Xavier, who will explain in detail what you see in setup one.
Okay, so will show you on a slide the diagram of the setup I will play with and to present you how it will work. Here we are. So as you can see here, we do have a very simple bench with an optical light source that is a single mode fiber with a diode laser. And then the light is collimated on a reference on the deformable mirror, and the light is coming back. And there are two optical pathways. One optical pathway is a far field camera with a microscope objective in order to have a clear view of the PSF given by the deformable mirror and the lens. And the other pathway through the beam splitter is the pathway for wavefront center. And the light is collimated by the lens. And the combination of the two lenses give an optical conjugation between the deformable mirror and the wavefront center. So the wavefront center is measuring the wavefront. From this wavefront measurement, of comment is calculated and then sent to the deformable mirror in order to have the correction of the aberration. The quality of your adaptive optic system will mainly depend on the wavefront center accuracy, for sure, because the wavefront center is the master of this setup. And for sure, it will depend on the deformable mirror linearity and hysteresis. The adaptive optic software has to be a very good one too. And something that is quite important in that setup is in adaptive optic setup is the optical conjugation between the deformable mirror and the wavefront center. Let's have a look of the bench directly, the real bench. Okay, here we are. So, as I told you just before, we do have the source here, the single mode fiber. The light is collimated by this lens on the deformable mirror, this one, and the light is coming back. And here you have the far field camera with a microscope objective in order to see the PSF. And here you do have the wavefront sensor with the lens to collimate the beam and the wavefront sensor here. Okay, let's go on the software right now. So let me present you the software. So that's the main windows of the WaveTune software or adaptive optic software. And here you have three main areas. One area for the control the deformable mirror, and you have the zoom here. An area for the wavefront that is measured, and you have the zoom there. And the last one is the far field camera, where you have a zoom on this part here. So right now we do have 0 voltages on the deformable mirror, and for sure with 0 voltages on the deformable mirror, the shape of the wavefront is not flat, not totally flat. The residual error is about 200 nanometers. And with this aberration, for sure, the point spike function is not just a perfect PSF, but an aberrated beam. Now, let's go to the first step of an adaptive optic system. And the first step is the calibration step. So, what we are doing now is to make the calibration of the adaptive optic system And for that, we are going to push and pull on each actuator, and the wavefront sensor will learn how the mirror is moving for each actuator. And what we are going to do, what we are doing right now is to it's a learning step where the mirror, the wavefront sensor will learn each influence function of each actuator. At the end of this step, the wavefront sensor will be able to know, and the software will be able to know what should see the wavefront sensor when we put a certain set of voltages on the mirror. But what we want to have at the end is the inverse. The wavefront sensor will measure a wavefront that is with aberration, and we want to calculate the command we have to send to the mirror in order to correct for those aberrations. And it's the step of inversion of what we are measuring right now. That is the interaction matrix. So we are close to the end of the measurement of the interaction matrix. 45, 86, 87, okay, 100. So now it is finished. Calculation for the aversion is done, and let's see the result here. We do have on this window, you can see, and we can see each influence function of the actuator. Here there are 52 actuators, so we have measured 52 influence functions. Thanks to this interaction matrix, we invert this matrix in order to get what we call the common matrix. And through this inversion, we are able to determine eigenmode of the system. And as you can see here, eigenmode, the first eigenmode of this system are very close to Wernicke polynomials. Here we have tilt, astigmatism, a second astigmatism, a comma, a second comma, a trefoil, the other trefoil, and here you can see something that is very close to spherical aberration. And when you are going through all these eigenmodes, the last eigenmode are a very high spatial frequency in order to correct very high spatial frequency aberration. So we have now a common matrix, so we are able to make a closed loop. For this closed loop, I've decided to have a continuous closed loop, so we will run and run and run, and I fixed the gain to 0.5. So each iteration, the system will correct 50% of the aberration, or residual aberration. So I will close the loop. So now I'm just in measurement process. I will close the loop when pushing on this button, and you will see here the waveform that will become a flat waveform, a perfect waveform, and you will see the result of this correction on the PSF on this screen. Let's go. First, second, third iteration, and now you can see here that we get a perfect PSF, an airy shape, airy disk, and you can see here that the RMS value of the residual error is 15 nanometers RMS, and you can have here the shape, the final shape of the beam, the phase of the beam in front of the wavefront sensor. And you have a very well correlation. The wavefront sensor say, okay, the beam is quite perfect. And here on the PSF, you can see that the result is virtually with no aberration, because you can see a perfect periodic and aberration, diffraction limited pattern. I would like to show you now what you can do with a very good deformable mirror and very good adaptive optics system. And to show that, I will just present you the correction of the aberration, but only with one measurement and one correction. And I will change the gain to put a gain of 1. That is to say that the wavefront sensor will measure all the aberration. The software will calculate the command and send the command to the deformable mirror, and we will see, and then the software will stop, and you will see the result with only one iteration. That is to say, an open loop configuration. The result of this. So let's go. Oh, yeah, let's go. We do have here the aberration because I've resetted the voltages on the deformable mirror, and I will push this button, and now we will have one measurement, one calculation, and that's it. And you can see here that with only one measurement, we can reach the same value and the same quality as we do have in closed loop. That is to say, that all the system here is quite perfect. The wavefront sensor is measuring the right aberration, and thanks to the very high linearity and virtually no hysteresis on this deformable mirror, we can reach the right shape only in one measurement. It's something that is quite unique here in the field of adaptive optics, and that is to say that this mirror is very well adapted for all open loop process that can be used in microscopy. So I've finished this presentation, so I will be happy to answer your question.
All right. So, do you hear me correctly, Xavier?
Yeah.
So, first question: how critical is the optical relay between the deformable mirror and the wavefront sensor on your setup?
The conjugation, the optical conjugation between the deformable mirror and the wavefront sensor is very important for different reasons. So the first reason is if you don't have the optical conjugation between the two these two elements, when the shape of the beam at the wavefront sensor location will change during the correction process. For example, if you have some astigmatism to correct, the shape at the beginning will be an elliptical shape, and at the end of the correction, you will have a round shape, circular shape, and that is to say that at the beginning there are some place where you have some light, and at the end you won't have the light at the edge, and the opposite. In the opposite direction, you will have some area where you will have light at the end and not at the beginning. That is to say that you won't have a stable shape during the process. And at the end, you don't have the optimum correction you can reach with the system.
Is it possible to do AO in the sphere?
Oh, of course, adaptive optics systems are really not dependent on wavelengths. If you want to have a sphere adaptive optics system, you need to have a deformable mirror with a coating that is compatible with sphere wavelengths, and for sure you will need to have a wavefront sensor that is sensitive for sphere wavelengths. But you can find these two in our catalog.
Do we have time for a third question?
Yeah, one more.
How is the linearity of the wavefront sensor possibly affecting the stability of the closed loop? What the relation between the linearity of the wavefront sensor and the stability or performance overall of the closed loop?
Okay. If the linearity of the wavefront sensor is not perfect, you won't reach the right shape and the right correction as fast as possible. You will take more iteration to do that and to reach the right correction, and that is to say that the bandwidth, the correction bandwidth, will be dramatically reduced if you are using a nonlinear wavefront. And the same for the deformable mirror. If the mirror is not linear, the bandwidth will be reduced. The correction bandwidth will be reduced.
Okay, do you have no more questions? Then we're gonna. Yeah. Okay, there's one more question.
Okay, we have an interesting question from Andreas. He wrote that the interaction matrix was acquired as there was a aberration in the bench. We expect a better correction if the interaction matrix is acquired around the perfect wavefront.
No, basically no. In fact, when we are doing the interaction matrix, we are making two measurements for one influence function. One movement when we push on the actuator, and the second movement when we pull on the actuator. And to get the influence function, we subtract the two measurements, and the result of this subtraction give us twice the influence function amplitude of one actuator, and the static aberration is removed by this subtraction. So basically, we don't have better result when we do an interaction matrix around the flat wave.
Okay, thank you, Xavier. I guess we now are going to move to the second setup, and so Guillaume, the floor is yours.
Yeah.
Okay, so let's go.
The second setup is dedicated to astronomy. What you see in this slide is a system designed for very simple. It's a very simple adaptive optics system dedicated to 1 meter diameter telescope in PQED, and we did a demonstration which gave us nice results. This bench is as simple as possible. We have on the upper left the telescope focal plane. So basically, the system is installed in the focal plane of the telescope. The beam is then reflected by a mirror. It enters a lens, so the beam is collimated on the deformable mirror. The beam is reflected on the same lens, another lens, but which has the exact same characteristics as the first one. So we create on the scientific camera pass the exact same focal plane than it was before the system was installed, except the fact that now the beam passes through the deformable mirror. You can see in the system that we have a beam splitter that is used to send part of the light into an optical path that into, of course, the wavefront center. If we just see in detail of the component here in the system, so we use in the system a piezoelectric deformable mirror, which has 43 actuators. It's a very nice mirror because it can be tuned up to 2 kilohertz. So wavefront sensor, it has only 15 by 15 microlenses because this application needs to be fast and we have a lot of time and not a lot of light. So we need to decrease at most as possible the number of microlenses. And the wavefront sensor is able to be run up to 1 kilohertz. As a scientific camera, let's use a very simple camera from Basel, and we use the same software that Xavier used just before for the setup lab. Just a small slide of what we obtained at Pic de Midi with this system. At this time, it was in 2017, as the planet Mars was very far from the Earth, less than 4 arcseconds. But we managed to increase very clearly the resolution on the planet. You can see very clearly that the image is really there with our system was on. So let's just now present you with the camera the setup. So try to go on the top here. So you may recognize here the deformable mirror. This is wavefront sensor. We have the beam splitter here. So the focal plane of the telescope is here. Here in a flipping mirror, I can remove it just for the video. So the beam goes this way to the deformable mirror and to the scientific camera. And here, the beam splitter is used to send part of the light on the wavefront sensor. As you see here, I have a flipping mirror in order to use an internal source of the system to do the calibration, as Xavier said. And when the calibration is done, just have to flip this mirror off in order to see something coming from the telescope. You have to have here a lot of imagination because I don't have a telescope here. The telescope is just a simple lens. And as a star, I use an output of a single mode fiber. So this is the star, the telescope, and then the focal plane of the camera is here. Okay, we start the demo with the flipping mirror in position in order to see the internal source, and then you'll see what happened when I open the flipping mirror. Just a small word here, you'll see that we will create turbulences in the air using just a heater. It's a very simple wire with a power supply, so it creates heat. You see that we'll be able to create the turbulence created by this. So let's fix the camera here, and now we'll focus on the software. So Philippe, can you please share with me all of this? Thank you. No, it's not. Okay. Yes. Yes. Okay. Thank you. So as you may can recognize here the same we presented just before, except that here the electrodes of the deformable mirror are set very differently than before. As is a piezoelectric deformable mirror, the actuators are placed in rings. So we have 4 actuators here and 3 to the exit at the outside. and we have the wavefront measurement here. So what we see here is, I don't know if you can read this figure, is 19 nanometer root mean square of wavefront error, going from the fact that here the mirror is set at the intermediate level. This mirror can be driven between 0 volts to 200 volts, so the medium position is 100 volts on all axes. Here on the left part, bottom part, I have an image acquired by my scientific camera. This is something quite blurred because, of course, of this aberration. So same demo than with that here. I can just click on here in order to close the loop. And as you see very clearly, the mirror now changed, and the residual wavefront is now below 5 nanometers. And now the image is sharp. Why is it not a narrow disk here, a narrow spot? It is because the internal source is a multimode fiber. So what we see here is the core of this fiber. I can redo the same demo and just come back to 100 volts on all actuators. The image is blurred. I can just write here in order to get a perfect image on my internal source. So now let's stop the system here. We know that the position is at its best for only the internal calibration for the system. Let's open the system to the external source. So I just flip the mirror. So we can see here now the stop. And what we can see also is that the wavefront changed. It has changed because the lens I used has some aberration. And that's the same case for a telescope. You have never a perfect telescope, perfectly aligned with perfectly polished mirror. So the telescope itself can have some aberration, can create some aberration independently of the atmosphere turbulence. So by doing this, I just have to just close it up again. And here, by clicking just one button, I can remove the static aberration coming from my telescope. Again, the wavefront error is now less than 5 nanometers. And the spot is now very close to narrow spot. What I can do now, I can do here a beam checker. I love this feature here because I can, in real time, change the wavefront target. I'm sure you remember the equation. If I change in real time the wavefront target, the wavefront measurement will immediately create a difference with this target, which changes the mirror shape. So if I change it, for instance, and ask the mirror to create some coma, so in closed loop, here, the coma is applied to the system using a change on the predefined targets. Okay? So here, by adding 200 nanometers of coma, the residual is still below 10 nanometers, which means that this deformable mirror is able to create 200 nanometers of coma very easily without adding some additional errors. But what I can do now is stop the closed loop. So now I'm in open loop and try just to reset to 0 in open loop. As you see, the wavefront that is now measured by the wavefront sensor is not 0, which means that when I ask this mirror to come back to its previous position without any measurement from my sensor, it did not come back to this position. And this is typically a problem because this mirror is a piezoelectric mirror. So everybody knows that piezoelectrics have a lot of hysteresis, drifts, and this kind of mirror are very nice to be used for fast adaptive optics, but in closed loop. You can't rely on such mirrors for open loop application. So let's now just push on in order to remove the small residue, control the system in closed loop, and retrieve a perfect error. So now my static aberration coming from my telescope are corrected. I can add my heater. So I just push the heater above the optical beam. As you see now, because of the heat created by the wire, the wavefront change, and the wavefront sensor is able to see the change, and of course you can see its influence on the focus spot here. So, in order to try to run adaptive optics on this kind of thing, I will change a bit the parameters of the software in order to be as fast as possible. So let's go to fast settings here, okay, and then let's try and see what happens. So here we have a lot of fluctuation, and when I click on, the star remains perfectly stable. And even if I remove the air with my hand in order to create turbulences, as you see, the star is completely stable. And the mirror change, but the residual wavefront is always at a scale of 15 to 20 nanometers in order to create a diffraction limited spot on my scientific camera. Then I can do some demo. If I stop the closed loop, you can see the perturbation created by the heater on the focus spot and on the wavefront. If I just click on, very quickly the system provides the wavefront, and we are here typically in an adaptive optics situation. This software is run actually presently on a very simple laptop. I have to broadcast this. So the frequency we have here is 275 hertz, which is not enough for Sky application, but we already tried to run this on a good PC and we obtained 800 hertz, and that was a configuration we used as a PQED to obtain the image of the planet Mars. The last thing I wanted to show you is what happened in case of instability. Remember the equation, I said that the gain in a fast closed loop system is a very critical parameter, because if it's too high, it may create instability. Let's try that. What happened if my gain is too high? Here the gain was 0.3. Let's try 0.5 and see what happens. Again, I just acquire the wavefront, reset my voltage to 100 volts, use my hand to agitate with the air, and let's switch on the system. Whoa, whoa, whoa. Immediately, the system is bad, because as a closed loop, as all closed loop systems, if you enter non-stability, you can't retrieve your previous system. The system can't recapture the stability. So the only thing to do is to stop, reset the voltages on the mirror, and just say, okay, my gain was probably too high. Let's try with 0.3. Just click 0.3, measure, and switch the system on. I think that's the end of this second set of demonstration. Maybe you have some questions. I will be very pleased to answer to you.
So Philippe or Jerome, do you have questions for Guillaume? Yes. Okay.
How important is it a special computer, or is it a regular computer?
No, it's just a Windows-based computer, but it was a desktop with a dedicated USB card, which allowed not to use the CPU to acquire images. So the CPU was 100% used to do the adaptive optics, but let's say it's an 800 euro computer. It's a good, simple computer.
Okay, thank you. No more questions.
Yeah, just a question, Guillaume. What do you think was the speed of the disturbance here?
Yes.
Because I can see you were running it at 270 hertz, right, for the adaptive optics. Do you think the disturbance was a 50 hertz disturbance, 100 hertz? And could you just talk generally about, like, you know, if you put this on a telescope, you know, the kind of disturbance you can basically correct? And because you kind of started the discussion on, like, oh, my gain is, let's put a lower gain because the disturbance maybe goes too fast and so on. So what's just I have a question on that. Yeah.
This is an interesting question, because if I focus on what happened when I increase the gain at 0.5, it's because the perturbations created by the heater were too fast compared to the speed of the adaptive optics system, and the delay between the time you acquire the image and the time you apply the voltages on the mirror is critical. If this delay is too long, you have to decrease the gain in order not to go into instability. So a rule by thumb is saying that if you want to correct up to 100 hertz perturbations, you need to run 10 times faster, which means 100 kilohertz, 1 kilohertz. Again, if you want to correct perturbation up to 100 hertz, you need to run at 1 kilohertz. Optimized system with a very complex command control loop allows to have better than that, but on the simple system, the speed of adaptive optics is critical. You have to be very fast in order to correct frequencies that are 10 times lower.
Okay. Okay, thank you. And so I think this kind of, I don't see any other questions here from attendees. So I think this kind of concludes the event. But I think what we see here in for the slides, the Q&A is set up too. So we see that we actually used a fast wavefront sensors that could do a kilohertz. Actually, for setup 2, we were not using the Mirao. I think we were using a different one, right? But anyway,
Yeah.
okay. Would you this setup you just showed, Guillaume, the cost of that setup, including the mirror, the wavefront sensor, and the software, was under 50K US dollars.
You're right.
Which is, you know, which is very, very low compared to, you know, what you could do just a few years ago with this kind of money. So we just wanted to point that out. Could we go to the summary slide, Patrick? There you go. So, you know, just to conclude here, you know, we presented, I think in this webinar, I hope everybody appreciated that, you know, we presented the principle of adaptive optics, you know, wavefront measurement, corrections, and so on. We showed some applications, you know, biomedical imaging, laser, astronomy. We showed 2 setups. The first one was with the Mirao deformable mirror, which is a magnetic mirror with continuous membrane. And the last setup was with a fast piezoelectric mirror, actually quite cost-effective DM. And so we kind of think you know, this is a very long subject, of course, but we see the main challenges of adaptive optics. You know, there could be hours of discussions on that, but we can see that, of course, there's a quality of components. You know, the measurement accuracy that we saw is very important. If you don't measure the right wavefront, you can't really correct it. But also, you know, the accuracy of the deformable mirror, the linearity, the fact that you need to do a pupil matching between the wavefront sensor and the deformed mirrors. And now, of course, all the software control, you have to write to do the right interaction matrix or calibration. You can act on the gain, you can do some beam shaping, you can do some open loop control, and so on. In terms of performance, we actually showed the first setup, we could close it at something like 15 nanometers. The second setup was, we could close it at 5 nanometer, although when, you know, you could see it vary from 5 to 13 nanometer RMS, but these are, I think everybody would agree that these are diffraction limited, basically, beams. And in the second setup, we could go to speeds that actually I saw something like 270 hertz with just a regular laptop PC. So this gives you good examples. And so to conclude, I would say, you know, Imagine Optic adaptive optic solutions are based on, we offer a large variety of wavefront sensors from X-ray, EUV to SWIR, going from 10 Hertz to a kilohertz. We offer two different kinds of deformable mirrors. There you go. These are the wavefront sensors. For the deformable mirrors, we offer two kinds of deformable mirrors. The Mirao 52 and the Alao Star. These are mostly the mirrors for bioscience, the Alao Stars for more like ultra intense lasers. And the software package is called WaveTune. It could be turnkey or it could be an SDK, but I think the important thing here is to see that WaveTune is very open to to actually most existing deformable mirrors and spatial light modulators. So if you have, you know, a mirror that we don't make, we can drive this mirror and, you know, give you a real adaptive optics tool. Next slide. And I think this is a very, nope, not this one, but okay, fine. This is kind of unique with our system, is the openness to all the deformable mirrors, basically. And then I think this will conclude it. I think Neshe probably has to run. Maybe there's a poll that we could run, but I think
yes, Philippe, I'm the one doing the poll today.
Oh, okay, Patrick, let's go. You can run the poll.
So 3 very short questions. The first one to tell us if you would like to receive a copy of the presentation we used today. So here we go. Please take a minute to answer the questions. Okay, thank you. The second question is whether you would like to receive more information on adaptive optics. Here we go. I also take this opportunity to emphasize the fact that there are 2 application notes that you can collect from the handouts in the GoToWebinar panel. So feel free to download those 2 PDFs. The first is on a high power and ultra high intensity laser. And now the last poll. Thank you for answering. And I would like to know if you're actively looking for a solution. Okay, thank you very much for your votes, and I hope you enjoyed this webinar. Philippe, back to you.
Yes, no, nothing else to say. I think thank you very much, everyone. We're of course available. If you have questions, you can send us emails. You know, you can find us at Imagine Optic website or Axiom Optics website, and we'll be happy to answer any of your questions. Thank you, and have a nice day.
Bye. Goodbye, everybody. Goodbye.